In this question, we are asked to investigate polygonal numbers. So an r-sided regular polygon where r is a positive integer greater than or equal to 3, the nth polygonal number is given by this equation right here. There's lots more information in this question, but this is the main thing that you need to use here is the formula for any polygonal number. So for triangular numbers, verify that P3 of n equals this. Okay, so for triangular numbers, that means r equals 3, and we just plug in r equals 3, and that's simply what we do here. So P3 of n equals 3 minus 2 n squared minus 3 minus 2 n over 2, and this obviously becomes n squared minus n over 2, and we want it to look like this. So we just factor out the n, and that's it. Actually, I think I made a mistake. That should be a plus right there somehow. Oh yeah, that's a 4, so that should be a negative 1. Negative 1 is positive, so factor that out, and you get this as required. Okay, next, the number 351 is a triangular number. Determine which one it is. It's a bit odd wording, but basically find the value of n, the term number. Okay, which triangular number is this one? So you just set that equal to the equation. Now this is a quadratic. You can solve by factoring. You can solve by graphing on your calculator, finding the points of intersection, or you can solve by quadratic formula, which is what I'm going to do. So let's multiply both sides by 2, and that's going to be 702 equals n times n plus 1. 0 equals n squared plus n minus 702, and you can factorize this, but it's not easy to see. So let's just use quadratic formula. We got negative 1 plus minus root b squared minus 4ac over 2 times a, right? And let's just type that into the calculator. So I'm going to make a fraction. And on the numerator, I'm going to have negative 1 plus. I'm going to do the plus first, then the minus later. 1 minus, don't even need to simplify, just type in the numbers as they appear here. Okay, and then 2 on the bottom. That gives me 26. And if I put in a minus sign instead, okay, negative 27. But of course these are triangular numbers, so it cannot be negative 27. It's just n equals 26. P3 of n plus P3 of n plus 1 equals n plus 1 squared. So that's simply using the formula again. The formula n times n plus 1 over 2. So here we got n times n plus 1 over 2. Now the same formula, just substitute n plus 1 into this. So you get n plus 1, and this becomes n plus 2. N plus 1 plus 1. N plus 2, right? So actually we're doing, I guess I should have written this first. It's called left-hand side equals that. Yeah, so we already have a common denominator. We just add these together and then simplify, and we should get that. I think when you're adding these two together, the easiest thing to do is actually factor out n plus 1. So we'll have n plus 1 outside of n plus 2 over 2. When we factor that out, we'll have an n plus that, which is equal to, actually we're trying to get that, so maybe that wasn't the most useful thing in the world. Let me scratch that out. Let's actually expand these. So we have n squared plus n squared plus 3n plus 2 over 2, which equals 2n squared plus 4n plus 2 over 2, which equals n squared plus 2n plus 1, and that indeed is n plus 1 squared. In the next question, it says state in words what the identity given in part B1 shows for two consecutive triangular numbers. So what we did in part B1 was we added two consecutive triangular numbers together. We got n plus 1 squared. So we could say the sum of the nth and n plus 1th triangular numbers equals n plus 1 squared, or maybe you can write it as the n plus 1th square number. And lastly, for n equals 3, sketch a diagram to clearly show your answer to part B2. So if the sum of these two numbers gives you a square number, you should be able to arrange it into a square pattern. Now we cannot use, probably shouldn't use color coding because you might scan, these tests might get scanned in black and white. So let's add together the nth triangular number for n equals 4. Okay, that means you're going to have the fourth triangular number is going to look like this. 1, 2, 3, 4. That's the nth. This is the fourth triangular number. Okay, maybe I can outline that so you don't rely on color coding. And for the n plus 1, the n equals 5, you can make a, let's just use hollow dots. Okay, I think this is about sufficient. Here's T5, fifth triangle numbers, or actually let's use the notation of the question. P triangle number 5, and this is P triangular number 4. Okay, so they create a square that is 5 by 5, or 5 squares. So I guess that's a sufficient diagram to show the result from part 2. In this next question we have, show that 8 times P3 of n plus 1 is the square of an odd number for all n and z plus. So let's just use the formula. We have 8 times P3n, so n is, n times n plus 1 over 2, the formula that we used from before. And let's simplify it and see what happens. So 8 divided by 2 gives you 4. We get 4n squared plus 4n plus 1. And we can actually, this factorizes to 2n plus 1 squared. That factorizes 2n plus 1 squared. And remember, that's an odd number, right? 2n plus 1. 2n is even, 2n plus 1 is odd. So that shows it. So I guess you could say at the end, therefore 8p3n plus 1 is odd for all n in z plus. Maybe you want to write down, 2 plus 1 is odd, just to illustrate it here. In this next part, we have the nth pentagonal number can be represented by this arithmetic series. Hence, show that that you can write it as n times 3n minus 1 over 2. So we can just use the formula from the formula booklet for the sum of an arithmetic series. So P5 of n should be equal to the number of terms, so n over 2 times the first term, which is 1, plus n minus 1 times d, which is 3. Okay, so we have, just to simplify this basically, n over 2 times 2 plus 3n minus 3, which is n over 2 times 3n minus 1, well, which is exactly the same as what is required. Okay, in this next question, by using a suitable table of values or otherwise, determine the smallest positive integer greater than 1 that is both a triangular number and a pentagonal number. So the otherwise, you could set up some complicated quadratic and figure it out that way using discriminant. But they suggest using a table of values, and that's pretty easy, so let's do it that way. So I'm going to type that into this calculator here. And HP prime under function, I just type in the two functions. So the second one is triangular numbers. The first one is pentagonal numbers, as we saw from the previous part. So you just type that in, and this works similarly with the TI-84 as well. Then I'm going to go to my tables, and I've got two tables of values. Just got to find out where they have the same number. So we got bigger numbers here on the left, so let's check these numbers with these. And you can see there's no 35, there's no 51 on the other side. It's a bit annoying, but it's a lot easier than doing the algebra and doing the discriminant. So if you keep looking, the first one that's in both lists is 210. Okay, now to show your work for this, you do not need to write down the entire table, just a snapshot of it, I guess. So let's do triangular. Let's just do a table for triangular numbers. Triangular, pentagonal, and we have n, and I guess we call this P3 of n. So our triangular number was number 20, so let's just do a little snapshot around 20, 19, 20, 21, 190, 210, 231, and for pentagonal, our answer was up here at 12. So let's do 11, 12, 13, and we have 176, 210, and 247. Maybe I'll circle them. And so the question says, determine the smallest positive integer greater than 1 that is both triangular. So you could say the smallest positive integer is 210. Simply that. In this last part, we are doing this proof by induction here. So a polygonal number can be represented by this series here. Use mathematical induction to prove that, basically prove this formula that we were given before, right? So we're going to use this with mathematical induction to prove that. So we'll start with the base case, which is n equals 1. We're starting with positive integers. So the left-hand side, well, actually it's not left-hand side. Not really. It's just, let's work it out with this one here and prove that you get this here. So if n equals 1, that means you're just going to have, n, actually let's put a 1 there, sorry. 1 summation m equals 1, 1 plus m minus 1, r minus 2 equals, this means you start with 1 and end with 1, so it's just one term. It's 1 plus 1 minus 1 times n, that's not an n, that's an r, times r minus 2, that's a 0, so you just get a 1. Now let's do it with this formula here. R minus 2 times 1 squared minus r minus 4 times 1 over 2. That equals, the r's are going to cancel, and you're going to get a negative 2 plus 4 is 2 over 2, which equals 1. Therefore, it's true for n equals 1. Next, for this, we'll assume true for n equals k, that is PR of k equals r minus 2. We're just using this thing with a k instead of an n. K squared minus r minus 4k over 2 for some k in z plus. So next, let's consider n equals k plus 1. Alright, so n equals k plus 1, just use the series. We're going to have k summation m equals 1, 1 plus m minus 1 r minus 2. Sorry, k plus 1, right? So we want to use our assumption. So we want this to be k, not k plus 1. So we can take the k plus 1th term out of the summation. So this is the same as k. That's a pretty poor sigma sign. M equals 1, 1 plus m minus 1 r minus 2. It's the same as that summation plus this with k plus 1 plugged in. Okay, so we're going to have 1 plus k plus 1 minus 1 times r minus 2. Okay, and this part is just our assumption, right? So we can replace that now with this result. So then we have r minus 2 k squared minus r minus 4k over 2 plus this here, which is just 1 plus k times r minus 2 by using the assumption. Okay, now typically with these questions you want to get a common denominator, so let's do that. So it's all out of 2, and this is now doubled. We're going to have 2 plus 2k r minus 2. And we're going to have to do some simplifying here. So let's back up a second and let's consider our goal, which is not really part of the proof, but it's what we're working towards. We want this with a k plus 1. So what we want is r minus 2, k plus 1 squared minus r minus 4, k plus 1 over 2. That's what we're working towards. So let's try to make that happen. And let's look at what we have right now. We have r minus 2k squared. We want a k plus 1 squared. We have an r minus 2 over here, so we can actually factor out r minus 2 from this first and last part. So let's do that first. And what we have left over is k squared plus 2k. So we're almost there. And so we factored out that from that, and we have everything else is still here. R minus 4k plus 2. So we want k plus 1 squared. This is almost k plus 1 squared. We just need a plus 1 there. So let's make that happen. Let's just add in a plus 1, and we'll subtract something afterwards to counteract that. So we added this plus 1, that gave us an extra r minus 2, so if we do that, we gotta counteract that by subtracting an r minus 2 on the end. So now this part is what we want. We want k plus 1 squared. And this part here, we want r minus 4, k plus 1. So we have r minus 1, 4, but what we can do, and this is an r minus 2, we want that to be an r minus 4, but actually, if you look at it now, this is like a positive 2 is like a minus negative 2. So we can actually put that inside this bracket here. Okay. So that's going to be the same as minus r minus 4, right? Because negative 4 becomes positive 4, which is what we have here. We have a 2 minus 2 plus 2 is 4, right? So these are the same. I just grouped it into a bracket. And then we can factor out r minus 4 from those two terms. And so we have r minus 4, and we factor that out, we're left with a k plus 1, which is what is required. I guess I should write now, maybe write PR k plus 1. Therefore, it's true for n equals k plus 1. So it's true for n equals 1 and n and true for n equals k implies true for n equals k plus 1. Hence, the result is true for all n in Z plus by the principle of mathematical induction.